Before we get started, I want to give a shout out to another podcast in the mobility space that I think you'll enjoy, the Rideshare Guy podcast by Harry Campbell. Harry has become a trusted expert on all things rideshare, and he may be the only person ever to have driven for Uber and also interviewed Uber's CEO on a podcast. On the Rideshare Guy podcast, Harry interviews a wide range of industry and thought leaders in the rideshare and mobility space. You can find and subscribe to the Rideshare Guy podcast on Apple Podcasts or wherever you listen to your podcasts. This is Smarter Cars, a podcast about autonomous vehicles and the future of transportation. Welcome to Season 4. This is your host, Michelle Kairouz. Today we're talking with Drew Gray, the CTO of Voyage, to do a deep dive on the current state of deep learning in autonomous vehicles, including the new project sponsored by Voyage called Deepdrive, which aims to accelerate research into reinforcement learning in autonomous vehicles. Drew, welcome to the show.
Thanks, Michelle. Good to be here.
So can you start by telling us a little bit about Voyage and what you're working on?
Yeah, absolutely. So Voyage is a self-driving car company, and we focus on building the software that enables autonomous transportation. We were founded in 2017 with a mission to bring self-driving cars to those who need it the most.
So where are you operating today? What was the use case that you guys decided to start with?
Yeah, so we sort of have a unique approach on it where we look at areas that actually have transportation problems that need a unique solution, where I think if you look at self-driving cars, through a product lens, it's not obvious that what a city needs is an additional car on the road, with so many options with Uber and Lyft. And, in my hometown, San Francisco, you have the Muni and the BART and so many ways to get around. What we found, there's certain areas in the world that this isn't true, and there's people that are really suffering from not being able to move around, don't have the mobility that people do in cities. And one of the best examples of that is retirement communities, where they're usually big and really spread out, and the demographic are losing their ability or their desire to drive. And it's just such an obvious place to bring a transportation service, and self-driving makes a lot of sense there.
I can definitely see that, as you get older, it would be super helpful to have someone drive you around. Where are you currently operating? What are the retirement communities that you're in?
So we're talking to a few. We're currently deployed in two of them. There's one in Florida, the biggest retirement community in the world, actually, called the Villages. Mm-hmm. And then there's one in San Jose that's just in our backyard where our headquarters is in Palo Alto here. That's also called the Villages, although they're unrelated. I think it's just a great name for a retirement community, I guess.
I didn't realize that they were unrelated. That's actually really funny. So what are some of the characteristics of a retirement community from a self-driving perspective that makes it a constrained problem set for you? They're private roads, not public roads, and what are some of the other characteristics? Yeah,
there's sort of two different answers. I think an interesting one is to answer that through a technical perspective. Mm-hmm. One of the reasons why self-driving cars is such a difficult problem, it's rather obvious, but it's in perceiving and understanding the environment around you, right? And in self-driving cars, this is the computer vision or the perception stack. And although deep learning has, really revolutionized this part of the self-driving car stack, it's still not quite as good as humans. So we don't really see and understand and predict the world as well and as quickly as a human does. Because of that, even with the state-of-the-art approaches to self-driving cars, there's still quite a bit of uncertainty in the environment. So where is this vehicle and how fast is it going and what will be its next move over the next 10 seconds? Something that humans just do so intuitively. Self-driving cars can do that, they just can't do it as accurately. So if you're in a complex city with high speed differences and you need to make really quick, assertive actions, it's really difficult to move through an uncertain environment, I think being assertive in an uncertain environment is almost a definition of being unsafe. What we found in the places that we are in, like the retirement communities, is the speeds are relatively low, 25 miles per hour tops. There's not dense traffic. Most of the junctions are rather simple four-way stops and things like that. And so even with uncertainty in sensing, you can still make safe decisions, and you can still get from A to B really comfortably.
And have you had to make any infrastructure improvements to operate in the two retirement communities that you're in? Like, are you relying on any V to I type connection, or are you just relying on this constraint problem?
Yeah, we actually have prototyped some things like that, and I think as self-driving cars become more and more common, I think the infrastructure will catch up. But you really just need to rely on what's there already, because you need to share the road with other vehicles that don't have this capability.
What about weather? Florida and California seem relatively good on the weather side, although I think you get thunderstorms and rain quite frequently in Florida. How do your cars drive in that weather?
So light rain is totally fine. The problem is when there's really heavy rain is the main sensor in a self-driving car is a LiDAR. LiDAR and cameras are the two main sensors, right? And for cameras, there's no problem with rain. But for LiDAR, the laser can actually refract through the water drops, and it gets a little bit difficult to see the world around you. So for now, we're sort of operating in fair weather. Although sensors are getting better and better every day, and I think this problem will be solved with better sensing. Radar is another great sensor for cars, and it can see through fog and heavy rain because of a longer wavelength. So as LiDARs and radars change and adapt to less highway applications and more city applications, I think we'll see that rain will affect things less and less.
Can you take us through the whole stack that runs an autonomous vehicle? You mentioned earlier perception and some of the advances there, but from these sensors that you're mentioning, the LiDAR, the radar, the cameras, all the way through to the car driving, can you just review for us kind of what are the pieces of the stack, and what are they trying to do?
Sure. So a lot of times people talk about the stack and they picture it vertically, which is kind of why you call it a stack. So imagine at the top is where all the sensor data comes in. You have radar, and you have camera, and you have LiDAR data. The first module is called perception, and perception's job is to make sense of all the sensor data, find all the patterns, detect all the things around you. So vehicles, pedestrians, bicyclists, everything around you that's moving, and then to track this through time and give you state information, so position and velocity and heading, what part of the map are they on, and things like that. Once the environment is understood, this gets handed down to a module called prediction. And prediction's role, this is one of the hardest problems with self-driving cars, actually. Prediction's role is to basically evolve these trajectories over the next 4 or 5 seconds. So if there's a vehicle in the lane to your left, and they start to move a little bit toward your lane, are they switching lanes, or are they just wandering in their lane? It's making decisions like this. Once you have these predicted trajectories and sort of the future of the world unfolding around you, the next job is decision making and planning. So looking at this vehicle to your left that's changing lanes in this example, your decision making would be that's a lane change, and your planner would slow down. So it would plan your own trajectory through time. And then the last module is control, and this will track your trajectory, make sure that you execute the plan that you thought you would, and interface directly with the vehicle. And then that sort of closes the loop, and the vehicle moves, and the sensor data updates, and that's the self-driving car loop.
When you look at that, there's perception, prediction, planning, and control. Which pieces of that would you say are sort of largely solved, and which pieces have the most remaining challenges as they're being articulated today?
Yeah, that's a really good question. So for a long time, and if you asked me that question maybe even a year or two ago, I would tell you perception is the hardest part by far. My background is actually in planning, but my whole career I've been actually focused on perception because it's been so difficult. And this is where machine learning has had the biggest impact. So the role of deep learning in self-driving cars has really only touched the surface. It has really revolutionized the perception stack, and it hasn't played a big role further down. But because of that, because perception, and I would definitely say perception is not solved. We talked a little bit about how there's still a lot of uncertainty in the environment. I think now that perception is getting better and better, I'm starting to realize that it was masking maybe the most difficult issue, which is in prediction. So yes, I can now see the environment and I can see that there's vehicles and pedestrians and bicyclists around me. But the hardest part is knowing exactly where these objects are going to, because there's a lot at play. There's context. If you're standing next to a crosswalk, you're likely intending to go the same exact posture. If you're standing at a bus stop, you're probably not intending to go. And there's the social dynamics, like waving people and nodding that you see someone. So it's all of that stuff, I think, that becomes the really hardest part of the problem now.
Yeah, when you have independent agents, whether it's a child, an animal, someone on a bicycle, you can say, 99 times out of 100, it's likely that they're going to do X, but what about that one time that they're doing something totally different? And we all, we've all had that moment where you kind of start to cross the street and then you go, oh, no, I left my keys at home. I have to go home. And you turn around, and so we're not all that predictable.
Yeah. Yeah, the world does seem quite unpredictable. So I guess it makes sense that predicting is the biggest challenge.
So you talked about these as modules like perception, prediction, planning, control. How does Voyage work with those modules today? Is each one kind of separate, or how do you think about that code? You mentioned there's some deep learning with respect to the perception module. Are you able to see the modules kind of separately? Do they operate separately, or how should we think about that?
Yeah, so they can be viewed separately, and the way I describe, the way I describe the modules is sort of industry wide, whether you're approaching it with a heavy machine learning focus or not. So you can think of the modules separately, but they have interfaces where they pass data between them, right? So the perception, for example, could create a list of objects around you with classes and then send it down to prediction. Part of that interface can also be a learned interface, though. So you could also ask the machine learning algorithm to learn features in the environment that would be important for prediction to be more accurate, right? So I think a lot of people, the way they talk about self-driving cars now is, at least something I've noticed, is there's people that describe the stack as either sort of classical modular approach or some deep learning AI approach. In reality, they're really very mixed. So you can still describe a system in a modular way, but you can have deep learning and machine learning learning features and connecting the modules in ways that weren't really there in classical approaches. So the way we do it at Voyage is a little bit like that, where we do have modules and we do have teams focused on making these modules better, but we also have a lot of data-driven ways to make sure that the vehicle is working end to end and you're not just building them in isolation.
And when you say data-driven algorithm, is that in contrast to a more heuristic rule-based algorithm, or how does that work?
Yeah, exactly. When I say data-driven, I mean the power of machine learning is rather simple to understand. It's just that let the data show you the representations that are important, right? So if you're building a detector to find a car, for example, the human might say, the features are the wheels are down, the windows are up, they're usually this size, they're not in the sky, they're not below the road. So you can kind of come up with things that are just generally true about cars. But there's thousands and thousands of more features hidden in the data, not necessarily human readable, that'll do a much, much better job. And that is really why deep learning has been so effective, because you initialize a neural network with literally zero understanding of the world. And as you show it data, it learns what representations are important.
It's so amazing when you think about the advances that have happened in that regard since 2012.
Yeah, really.
Yeah, maybe you could get into that a little bit more and tell us about the different types of deep learning. I know there's like supervised and unsupervised, or maybe semi-supervised. Can you maybe lay out that spectrum and help us understand how those are being applied in the self-driving stack?
Yeah, absolutely. The most common approach that deep learning is used in self-driving cars right now is a supervised learning approach with a convolutional neural network. A convolutional neural network is mainly a network that works on images, whether it's a camera image or a LiDAR image. You can think of that as an image as well, or a radar even. So it's supervised in the sense that someone goes through and labels everything in the scene. So imagine a camera image. You can ask someone to go put a box around every car that they see. Then you give this same image to the network, and you ask it to predict where all the cars are. And now you have a prediction, and you have the ground truth. And you can use these to compare and find an error. And obviously, the first time the network tries this, it's going to be terribly wrong. So it'll say you were wrong by this much for these reasons. And the network will then do back propagation, which is the mechanism the network learns, and it will update. And pretty soon it'll get more and more accurate, and it'll almost get to human quality, where you say, show me all the cars, and it'll just put boxes around all the cars. So supervising in a sense that a human label all of the data, right?
And that's that's what's kind of time intensive about it and data intensive. And people talk about systems getting better the more data they have. It has to be good data that's labeled. But if you have a million pictures of a cat and you label it, you can do a better job at this supervised learning than if you didn't have a million pictures of a cat to show it. Is that fair?
Exactly. Yeah. And it's the same as learning in humans, where there's a big difference between learning and memorizing, right? So just like the cat example you used, if you show a million pictures of a cat and then it starts to get it right every single time, it has just memorized what a cat is. Then if you show a different species of cat or a different dog, it won't learn at all. So what that means is it didn't generalize. And so why it's such a big data problem, the way people describe it, is to generalize, you need so much variety in the data. So you'll need to see the car driving during the day, the car driving during the night, in different weather, different types of vehicles. The more and more variety of data you show it, the more it generalizes and the less it's memorizing a specific problem.
I see. So it needs to see the different pieces of the car, what it looks like from the back, the side, the top, all different angles, that kind of thing.
Yeah, it needs an unusual amount of data. I think one of the next biggest breakthroughs would be in learning with much less data. And just like you mentioned with, humans, even a baby, you can show them a laptop, and they don't need to see that laptop from every single angle to know what a laptop is at that point. And that's not the case with neural networks right now. You actually have to show it everything. So they are powerful tools, but they're not generalizing the way we want them to right now.
Moving along the spectrum, what are the other types then of ways to do these algorithms that are less supervised?
Yeah, then there's less supervision. There's like you mentioned, there is unsupervised learning, and one of the common uses of unsupervised learning in self-driving cars is what if to answer the question, what if there's an object that you didn't specifically train on? So in our communities that we're in, there's actually a lot of wild turkeys. I don't know if you've seen some of the videos we've posted, but more and more of them. So we've been seeing turkeys run out into the road, and we actually don't have neural networks specifically trained to detect turkeys right now, although we are currently building a data set to do this. So just because we don't train on turkeys doesn't mean we can hit them, right? You still can't hit anything. And so this is where unsupervised learning comes in. So unsupervised learning can find its own patterns in the data with no supervision. And that's what we do with objects that aren't specifically trained on. So if a trash can rolls into the road, or if there's a deer, or if there's a turkey, we'll actually cluster the sensor data and build an object out of it. And then we can predict its motion and do the rest of the self-driving car stack, even though we don't exactly know what that is, because we've built a pattern out of the data, if that makes sense.
So you see the turkey, you don't know if it's more like a dog that you shouldn't hit or a paper bag that you should run over, but then it moves or it has certain other characteristics that make the algorithm think it's more like a dog and don't hit it.
Yeah, even if it is a paper bag, as long as it's a big paper bag, we'll likely stop at this point. If we specifically detect it. So if the deep learning powered computer vision system fails to see something because it wasn't trained on a specific class or just the long tail of data in general, right? If there's something in the road, whether it's moving or not, the self-driving car's program could just not hit it. And so we could be in a situation where you stop for a paper bag and be rather conservative, but then there's ways to get around that. So it's just a way to make the overall system much more safe.
And so the difference between unsupervised learning and supervised learning is whether you have specific data that the algorithm's been trained on. And is that what you guys call ground truth, where you have something to compare against?
Yeah, exactly. Yeah.
What is semi-supervised learning, or is there something kind of in between? And maybe that takes us into reinforcement learning.
Yeah. So reinforcement learning is a really, really interesting approach. And to me, it's like the one approach that deserves to be called AI. And the way it learns, AI is such a broad topic, right?
Yeah.
The reinforcement learning, like truly is. So the way it works is it's always best to train reinforcement learning in simulation, because the idea is a balance between exploring and exploiting. The best example of reinforcement learning, I think, if you're in like an RL 101 class, would be the game of blackjack. So let's just initialize a policy that says always hit no matter what. I don't know why I use this example. I'm not a gambler at all, but it just makes a lot of sense. So you have the policy, right? Always hit no matter what. Obviously, that policy is not going to work well. So you do that policy, which is the exploiting part. You exploit the policy you have. When the episode is over, so when the game is over, you probably lost, and you'll trickle back the rewards, and this reinforces the behavior. So why it's called reinforcement learning. Very similar to training the dog with food, where they do a good behavior, you give them a treat, and that reinforces that behavior. So pretty soon in the blackjack example, you'll start updating your policy, and you'll quickly converge on an optimal policy, but you still need to balance the exploration phase, so you're not stuck in local minima. So every once in a while, even though you think you should hit, maybe you shouldn't. And you might find that that's a better method overall. So the way that works for self-driving cars in simulation is, and this is why it needs to be simulated, you can initiate a car to start driving in the virtual world, and it could start, if it crashes, it loses points. If it succeeds, it gains points. And it could quickly reinforce good behaviors in driving. And the hope is one day you can program a vehicle end-to-end with some sort of reinforcement learning architecture to just drive a vehicle.
Two things come to mind that probably stick out in a lot of people's minds as well. One is the NVIDIA video on end-to-end neural nets with self-driving that came out maybe in 2016. And the other thing that it reminds me of is the Atari game where the algorithm learned to play Breakout and didn't know what the rules were and sort of taught itself a better way to play. Are those examples of reinforcement learning?
Yeah, they are examples. And you actually find a lot of reinforcement learning examples are in video games. And it's not because they're toy problems. It's because they offer such a rich simulated environment. So, a lot of OpenAI's work, for example, is done on video games. Even though the architectures and decisions these algorithms are making are pretty complex. I think it's worth noting that it's still a very researchy way to approach self-driving cars, and it's not the way we at Voyage approach it, or anyone really. A lot of people looking at things like this are trying to embed these ideas into the self-driving car stack without being just completely end-to-end.
So that's a great overview of the different types of algorithms. Let's talk about this difference. You're pointing out that the way that Voyage and all the other self-driving companies work at this point is as you described earlier with the modules, and there's some sort of deep learning maybe in perception, a few other spots. But they're certainly not doing this reinforcement learning, which thus far has been in kind of academic papers and video games and that type of research work. You guys at Voyage came out with a really exciting announcement this week about something called Deepdrive, where you're going to be contributing to this research. Can you tell us about the Deepdrive project, how it relates to this question of reinforcement learning or end-to-end learning, and what you guys are working on?
Yeah, absolutely. Speaking of reinforcement learning and simulators, we just released an open source simulator called Deepdrive. Its intention is to basically enable the research like this. So, driving is actually, inherently rule-based, where you study, in the U.S., you study the DMV guide and you have to take a test, right? But there's still such a big impact that machine learning can have, whether it's end-to-end or in just specific modules like decision-making. And every company I've been to, I've actually worked at 5 self-driving car companies, so I've been focusing on this problem for a really long time. And every company I've been to, I've been so surprised at the quality of engineers. There's just so many good people working on this problem. But I'm just in Silicon Valley, and the number of engineers in the world compared to the number of engineers working on this problem, it's almost negligible. The hope we were having with Deepdrive was to put this tool in the hands of anyone that wants to or that's capable of working on it, to really, really accelerate the development of machine learning's role in self-driving cars.
Great. So how does it work? The problem you're trying to solve is working on end-to-end or deep reinforcement learning, either for the whole driving problem or for individual modules, and you're hoping that by providing a sandbox for research that you'll advance that research faster by using your simulator in an open source way? Is that what you're trying to do?
Yeah, if you look at a lot of the breakthroughs made and a lot of the work being done in industries like computer vision is really like a model industry to me, where it's very open, it's a very level playing field. If someone makes a big breakthrough, it's published immediately, oftentimes with the code base. And you can immediately see where the state of the art is by looking at these academic data sets like Kitty or something. So it's our hope with Deepdrive is to sort of do the same thing, but for self-driving research. So if someone makes a breakthrough in an algorithm, right now, maybe the world doesn't know about it. Maybe they themselves don't know that they made a breakthrough because it's hard to compare it to anything. So we're hoping to launch a leaderboard alongside, or we have launched a leaderboard alongside, where we can build scenarios that we think are really tough and challenging. And that was the important part about releasing this as part of a self-driving car company that understands these challenges intimately. We can build into the simulation environment the things that are hard to solve. And then anyone capable could try to solve them. And we can have a leaderboard that shows where the current state of the art is and what were the recent technical breakthroughs and things like that.
So what Voyage is really adding here is its knowledge of the tough problems in self-driving from its own work and adding those scenarios into the simulator. And then it's open source, so anyone who wants to write an algorithm can upload it and see how it works and get some results and compare to what other people are doing? Yeah,
exactly. So, one of the famous difficult problems of self-driving cars is the unprotected left that a lot of people talk about. So that was our first launch scenario. So we'll be adding more and more scenarios over time, but 2 vehicles are oncoming, and your goal is to yield for them to make a left turn. So by building the simulator, by building really simple interfaces where you can immediately grab the sensor data, if you've worked on machine learning before, you'll find the data structure to be very familiar, and you can start actually working on, moving the state of the art forward. That's our hope with releasing this. And by making it open source, it's just part of giving to the community and being part of leveling the playing field. So people can go in, they can build their own scenarios, they can rearrange the world, they could change things that they see fit, anything to help them do their research.
And is there a data set associated with it, or is the idea that you don't need as much data because you're doing this reinforcement learning?
Yeah, the data set is sort of built into the simulator. So you can generate your own data in any way you want with any of the sensors that we have available. We don't have a data set alongside it that we've sort of pre-compiled, but it's pretty straightforward to collect any of the data that you would need.
And what will Voyage do? I guess this is publicly available, so anyone could take the results and work with them, or what is the value to Voyage of sponsoring this research?
Yeah, so what we're hoping is to one deep part of these breakthroughs. So the playing field, like I've been discussing, it's already pretty level. So if someone has a breakthrough, it's okay if other companies can see that. I think by Voyage being part of it, the engineers that are working on this type of research hopefully are more attracted to come work with us if they're looking for a job here, of course. But what we can also do is we can push the simulator towards a simulator that we think is important. So it has all of our requirements and all of our interfaces, the way that you access the map, the way that the objects and that the sensors are set up. So I think we could really build something where the research done in Deepdrive, we can see how it could be directly applicable to making our car drive better as well.
Great. So it's like a request for research. It's tailored to what you guys think are the key problems. You've talked about reinforcement learning, and that's kind of the focus, it sounds like, of Deepdrive. What would be done with it? I mean, I think you mentioned there's sort of two possibilities. One is sort of this full end-to-end network for self-driving where you kind of take sensor images in and driving inputs out. The other might be that you just use it specifically in a module. Where do you think the industry is heading if this project is incredibly successful? If there are developments and improvements in reinforcement learning, how would you imagine it might be used by the industry in the future?
Yeah, the way I think the industry is heading, so let's go back to the way we were imagining the self-driving car stack being this stack of modules vertically, right? And if you look at the interfaces between them, so let's imagine perception to prediction. Typically, you pass down a list of objects and their state, weighting, velocity, things like that. One way to think about that is you really just created a pinch point. So you have tons of data in perception with the raw sensor data, and then you force through a small bottleneck a list of objects. Maybe that is not the best representation of the world. Maybe prediction needs a lot more information than that. So the way I see the role of deep learning, AI, reinforcement learning, you can think of it as sort of, seeping down the stack where it now does the heavy lifting in computer vision, but can we actually learn these interfaces? Can we get rid of the pinch points? We already know that humans aren't the best at figuring out their own representations of the world. This is why machine learning is powerful in the first place. So what we're hoping with Deepdrive is to give people a platform to explore ideas like this. So it doesn't necessarily just need to be end-to-end, although that's really interesting in itself. But for example, what does decision-making need? They need the map, the list of objects. But what if you also had a huge vector of information that was completely learned from the environment? It looks like gibberish if you try to read it, but it makes decision-making 10 times better. And you could immediately integrate this into a real self-driving car with the same ideas at least, and it could augment or work with some of the heuristic-based rules. What we're really hoping is to see breakthroughs like that, where the power of machine learning and the potential of machine learning could be used in other places of self-driving cars.
So it doesn't have to be one or the other when you're talking about kind of heuristic rule-based code versus these algorithms. It could be a combination and kind of a more fluid relationship instead of a more rigid stack. Is that what you're thinking?
Yeah, Yeah, exactly. And it really should be a combination. Like we were talking about how driving is just inherently rule based. I'm a big fan of really exploiting the structure of your problem. So, for example, we know it's illegal to turn left across the double yellow line. If we already know that, there's no reason to ask a network to learn that. It's sort of a waste of data, a waste of time. Things like that could be encoded, which is really the value of having an HD map along with your self-driving car. You can encode rules of driving, and things that are difficult to encode, like the fluidity and variance of the environment, those things their representations can be learned with machine learning.
So one of the other concerns we hear people raise about using deep learning algorithms is this sense that it's a black box. There's a lack of interpretability and sort of that we don't quite understand why the car did a good job in one place or did a bad job in another circumstance. How do you think about that as we move forward with this academic type research going more in the direction of reinforcement learning?
Yeah, I think the concept of machine learning being a black box is sort of a carryover from the earlier days of neural networks, where people use neural networks to model systems that they didn't quite understand the structure of. So if you had a physical system and you didn't know the equations of motion, for example, you could use a neural network and you might be able to learn it. And this very much to physicists would look like a black box. Like, why would you do that approach? As neural networks got bigger and we started calling these networks deep learning, that same concept kind of carried through as if any neural network you can't interpret. I think there's so many more tools now and so much more understanding that you can actually visualize different results. And you've seen things from like Google Daydream, for example, or not Daydream, but the Google networks that create their, I forget what it's called, but you can visualize what the network is. I think they call it hallucination. So you see what the network is hallucinating, right? And you can actually probe deep into the layers of these convolutions, and you can see these are edges, these are corners, these are actually wheels. And then there's, of course, a lot of representations you can understand, but there's actually a lot of interpretability to these networks.
And what about the question of compute power, processing of data, memory? How do the system requirements, I know a lot of self-driving cars have a lot of compute power in the trunk, and there's a concern that the cost is high or the data requirements are high. How does that change as we move into thinking about more deep learning or reinforcement learning?
Yeah. Right now, basically these networks definitely require a lot of GPU power, and essentially what happens is every year NVIDIA comes out with a better GPU that's 10 times better, and then the networks have 10 times the requirements, and so it always just kind of stays level. The difficult part is, the cost of the GPUs themselves, and then the power requirements. So 4 GPUs, 250 watts, you have a kilowatt of power in the trunk of the car, and a lot of the heat that you need to dissipate and things like that. I think the best approach is you want to give the software team and the self-driving car company as much creative freedom as possible. And so right now, all the self-driving cars have all of this GPU power. As soon as you start getting close to the right solution where you don't need these big 10x changes, you can go to a much smaller, lower power part, like ASICs are specifically built to do things like this. So although there's a lot of big, expensive, and power-hungry GPUs and compute now, as soon as the problem starts to converge, I think that we'll see much lower costs of parts.
What does the next year or two look like over at Voyage? Are you going to continue to expand the different private communities you're serving? Are you looking to drive on public roads? What do you guys have in mind for the next few years? Yeah,
our goal is to expand in the communities that we're in. It's not necessarily that they're private roads or public. It's more of the type of community where there's not, like we were discussing, there's not great transportation options for people. So it's really refreshing to know who your customer is and to interact with them daily, and to work on on how the product should change and the way that they would use it. And so we're planning on working more and launching a service in the communities that we're in and expanding to additional communities and plus communities that look like the ones that we're in. There's master plan communities and office parks and small towns that all have really similar challenges. So the next couple of years, we're likely to go deeper into a product with the people who use it, as well as expand to find a growing customer base.
Great. Well, thanks so much for coming on the podcast. This was a really interesting education in all of this, and I look forward to seeing what happens with Deepdrive as that project moves forward.
Yeah, thank you. Thank you for having me.
Thanks again to Drew for joining us. You can find the show notes for this episode and all of our episodes on our Medium publication called Smarter Cars. If you're enjoying the podcast, please subscribe on Apple Podcasts or wherever you listen to your podcasts. Thanks again for listening. We'll see you next time.